Hello dear students, welcome to the 7th lecture of the lecture series on welded joints. In the previous lecture, you have seen the design of axially loaded unsymmetric welded connection, where the lengths of the welds were not equal, but the load which was acting on the weld was passing through the centroidal axis of the welds. In this lecture, I am going to teach you the design of eccentrically loaded welded connections, and then eventually we will solve some problems on the related topic. Now, since this is a relatively big topic, that's why I am going to divide the video lectures into two parts. In the first part, I'll try to explain how to design eccentrically loaded welded connections, and in the second part, I'll try to solve some problem related to the topic. Now, before starting with the design of eccentrically loaded welded connection, let's see what is an eccentric load. Now, suppose this is a plate. Okay, this is a plate. Now, obviously the centroid of this plate will lie at the center of the plate because the centroid is the geometric center of the structure or the plate. Now, since this is the centroid of this plate, now if I apply a load over here or over here, then the load is always passing through the centroidal axis. This is your x centroidal axis and this is your y centroidal axis, provided that your reference or the Cartesian coordinate system is placed at this point. This is your origin with positive y direction in this in the upward direction, and the positive x direction in towards this direction. Now, this is the centroidal axis as well as this is a centroidal axis. That's why when we are applying the load over here as well as over here, this type of loading or the line of action of the load is passing through the centroidal axis. That's why there is no rotation of the plate. That's why there is no rotation of the plate, and the plate is basically, or the welds should, if set freely, they should move in the direction of the load. Now, suppose I apply a load over here or at any point which is not which is not passing through the centroidal axis. So, suppose I am applying the load over here. This time you can see that the load or the line of action of the load is parallel to the centroidal axis. It is parallel to the centroidal axis, but it is at some distance from the centroidal axis. So, such kind of load which are parallel to the centroidal axis but at some distance from the centroidal axis, they are known as eccentric load. So, this load which is applied on this plate is known as eccentric load, and the perpendicular distance between the centroidal axis and the line of action of the load is known as eccentricity. This is known as eccentricity. So, this type of load which is at some distance from the centroidal axis, this is known as eccentric load. This load is eccentric and the distance is your eccentricity. Now, while defining the centroidal load, I have while defining the eccentric load, I have used a term centroid. Now, you people always get confused with the terms centroid, center of mass and center of gravity. Although all these three terms are completely different and they are not basically same in any manner to each other. So, let's see what is the difference between these three terms before moving further. So, first of all, your centroid is the geometric center of any structure, which is this point in our case. Secondly, we will talk about the center of mass. So, center of mass is a point where we assume all the mass of the structure to be concentrated. For example, if I am saying that this is your center of mass of this plate or this book, that means that all the mass of the book is concentrated at this point. So, if you try to balance this book at this at the center of mass, it will get balanced. Okay, it will get balanced because all the mass of this book is assumed to be at that point. You can also define the center of mass in another way, that if I apply a force on this book, okay, and if this book always move in the direction of the force without any rotation, this is very important, without any rotation, that means that the load is applied at the center of mass, or that point where the load is applied is center of mass. Now intuitively you will say that when I'm going to apply the load over here, the book will always move in the direction of the load without any rotation. So you will say that this point can also be treated as center of mass, but this is not the right answer, or this is not the right thing, because if you apply the load in this direction at this point, for sure the book will move in this direction. But in case I change the direction of the load, for example, this time I apply the load in this direction, you can see that the book is moving forward as well as it is rotating. So center of mass is a point where when the load is applied in any direction, it will always make the structure move in that direction without any rotation. So by this definition, this point will not be qualified as the center of mass. Only this point where I have balanced the book earlier, that point is your center of mass, because at that point, whenever you are going to apply any force in any direction, it will basically tend to the plate or the book will tend to move in that direction without any rotation. Without any rotation is important, because if you are going to apply any force at any point, it will allow the book to move forward, but the book will also rotate as in this case. But if I'm going to apply the force at the center of mass, the book will always move in the direction of the force irrespective of the direction of the force. Third thing is your center of gravity. Now this book is basically made up of n number of particles. Each particle is attracted by the force of gravitation in the downwards direction. Each particle is attracted by the force of gravitation. Now the resultant force or the overall force will act at some point and that point will be known as center of gravity. Okay, so you can assume that each of the particle is pulled down by the earth because of the gravitational force. Now what I'm saying is that the resultant of all these forces will act at some point, and that point will be known as center of gravity. In order to calculate the center of gravity experimentally, what you can do, you can hang this plate at some point. Okay, suppose I am hanging this plate at some point. Now your plate will always be aligned this vertical direction, which you can see your plate will always be aligned along the center of gravity axis. Okay, so you will mark a line like this. Now try to hang the book at some point other than this point, suppose like this. Again you will mark a line like this, because all the weight of this book will be aligned in the direction of the center of gravity. Now wherever these two lines are intersecting, that point will give you the center of gravity. Now while explaining all these terms, you have seen that I have always pointed at the center of this book, be it a centroid, be it a center of gravity or center of mass. That is because for this particular condition, all these 3 points are same. All these 3 points are same, because center of mass and the centroidal axis, the center of mass and the centroid will always be same for any structure, provided that the density of the structure is same throughout the structure. Okay, since the density of this book is same at all points, that's why its centroidal axis, its centroid or the geometric center is same as the center of mass. On the other hand, if the gravitational pull throughout the structure is same, then the center of mass will be same as the center of gravity. So since we are sitting on Earth and the gravitational pull in the vicinity of the book is same throughout its structure. That's why we can say that the center of mass and the center of gravity for this particular book is same. Okay, for this particular book is same. Now suppose I am having a structure like this, and over here I am having a gravitational pull of 9.81, which is meter per second square, which is the gravitational force of the earth, and over here I am having somewhat less gravitational pull, suppose say for example say 7.89 meter per second square. So for this particular condition, since the gravitational pull at this side is higher as compared to the gravitational pull on this side, that's why the center of the gravity will shift towards this side, because the gravitational pull is high at this side. Whereas the center of mass, since the density of this structure is same throughout the structure, that's why the center of mass will lie at the centroid of this structure, which is the geometric center. So we can say that if the density of the structure is same and the gravitational pull throughout the structure is same, then in that case we can say that the centroid, the center of mass, and the center of gravity, all these three are same. So since our welded joints are subjected to the eccentric load on earth, where the gravitational pull is same at all the points, and since the material of the weld are same for all the welds, that's why the density is again same, because the height of we are going to we basically assume that the height of the weld is equal to the thickness of the plate. So again the volume of the weld is same, and it is made up of same material. That's why the density at all the points in the weld is same. So we can, for our problem also, we can say that the centroid, the center of mass, and the center of gravity will all lie at the same point. So for that particular reason, we are going to calculate the centroidal point of all the welds. So let's start with the design of eccentrically loaded welded connections. In this figure over here, you can see that there are two different plates. This is your first plate and this is your second plate, subjected to a load of magnitude P acting vertically downwards. Now weld W1 is your weld 1 and W2 is your weld 2. Now for this particular condition, the length of the first weld is equal to the length of the second weld, for this particular condition only. G is the center of gravity of all the welds. This point is the center of gravity. Now as I explained you earlier, for our problems, we can say that since the density of the weld is same at all the points and the gravitational pull on all the welds is same, because we are basically using this type of structure on earth only, that's why we can say that the center of gravity is same as the centroidal point, which will again be same as the center of mass. Okay, now this structure is subjected to a load of magnitude P at some distance E. Since the direction of the force is parallel to the centroidal axis and is at some distance E from the centroidal axis, that's why this load is known as eccentrically loaded. This load is known as eccentric load. This distance E is known as the eccentricity. Now we don't know how to design a load, we don't know how to design a weld subjected to an eccentric load. However, we know how to design a weld where the load passes through the centroidal axis. So what we will do, we will bring this load at the centroidal axis, at the centroid, we will bring this load from here to here like this, And since we are bringing this load from this point to this point, in your freshman year you have already studied this concept in applied mechanics, that whenever we are going to shift a load, there will be a moment induced at that point. And the direction, since the direction of the load is downwards, that's why the direction of the moment will be clockwise. Okay, the direction of the moment will be clockwise. So again, you can see in graphically that when we are going to bring this load from at this point to the center of gravity or the centroidal point, then there will be a moment of magnitude m induced in the clockwise direction, since the load is acting downwards and it is towards the right of the point where we are going to shift the load. Now the magnitude of this moment will be equal to the magnitude of the load cross the distance e, or the eccentricity. This will be your magnitude of the moment. Now we will study the effect of these two, basically the load which is acting vertically downwards and the clockwise moment separately on the weld, because there will be a primary shear stress developed because of this load acting at the centroid, and there will be a secondary shear stress because of this moment. Now in these two figures you can see that I have shown the load separately and the moment separately. That's because we will study the effect of the load on the weld as well as the effect of the moment on the weld separately. Okay. Now as I told you, because of this load, since it is acting vertically downwards, there will be a shear stress induced in the weld of equal magnitudes acting upwards. Okay, this is your direction of the shear stress, and we will be calling this shear stress as primary shear stress. Okay, similarly there will be some torsion in this weld, and because of this moment there will be some shear stresses. We will talk about the direction of the shear stresses later on the slide, but we will call this type of shear stresses as secondary shear stresses. Okay, now the secondary shear stresses will be directly proportional to the distance from the centroid or the center of gravity. For example, since this distance is greater than this distance, that's why the magnitude of the secondary shear stress developed at this point will be greater than the magnitude of the secondary shear stress developed at this point. Now obviously this moment will basically tend to rotate this welds in the clockwise direction. That's why the direction of the secondary shear stress will be in the opposite direction, which is in this direction. And okay, so the direction of the secondary shear stress will be in this direction, and your primary shear stress will always act upwards like this. I'll draw it with some other color so that it will be more clear to you. If we talk about this point, this will be your primary shear stress and this will be your secondary shear stress. Now although we have studied the effect of this load and this moment separately, but we are going to calculate the resultant shear stress, which we will do by vectorially adding the primary shear stress and the secondary shear stress, and then we are going to further find out the size of the weld. Now in the slide you can see that because this primary shear stress is caused because of the load acting downwards, at the center of gravity of the weld, and it is uniformly distributed throughout the length, throughout the throat of the weld. The magnitude of the primary shear stress is same at all the points, and the magnitude of the primary shear stress is calculated as the ratio of the load acting on the at the center of gravity of the welds and the area of all the welds. This is the total area of all the welds. This is the total area of all welds. Okay, and this is the complete load. This load is acting at the center of gravity of all the welds. So this is how you are going to calculate the magnitude of the primary shear stress. It is quite easy because you already know how to design the welded joint where the line of action of the force is passing through the centroidal axis. In this particular case, the load is eccentric, because of which there will be a secondary shear stresses. This is because we have shifted the load to a point where the center of gravity is lying, because of which we have to basically introduce a bending moment, and this bending moment will cause the secondary shear stress. Now the magnitude of this shear, this bending moment, as I explained earlier, is P cross E, where P is the magnitude of the load applied at the center of gravity and E is the eccentricity of the load. It is directly proportional to the distance from G. This means that suppose I have a point over here and a point over here. Now since the distance of this we will call this point as A and we will call this point as B. Now since the distance of the point B from the center of gravity is smaller than the distance of the point A from center of gravity, that's why the magnitude of the secondary shear stress induced at point B will always be smaller when compared to the magnitude of the secondary shear stress induced at A, because the magnitude is directly proportional to this distance, and we will call this distance as R. And the magnitude of the secondary shear stress is equal to M times R divided by J, where M is basically the bending moment whose magnitude is given by this. R, as I told you, is the distance where you are distance of the point where you are going to calculate the secondary shear stress, and J is the polar moment of inertia. It is the combined polar moment of inertia of all the welds about the point center of gravity. So this is how you are going to calculate the magnitude of the secondary shear stress. And once you have the primary shear stress and secondary shear stress, you are going to vectorially add them both. This brings me to the end of the first part of this lecture 7, and in the second part I will explain you how you are going to calculate the polar moment of inertia or the combined polar moment of inertia of all the welds, and then I'll also explain what is polar moment of inertia. Then we will also see how to find out the center of gravity or the centroid of all the welds, and eventually we will try to solve some problems on this topic, and that will be all for the first part.